So let's talk about regular expressions. And there's going to be general regular expressions in the theory of computation, but then we're going to apply it to JavaScript. So in the theory of computation, the field of computer science, theory of computation, which is also, it covers complexity, basically deals with when you're doing a computation. If you're doing computation on paper and pencil with a calculator, you're going through steps. Step one, take these two numbers, add them together, write the result off to the side because I'm going to use that later. Then go to step two, then step three, you might go into a loop, and repeat steps. So effectively, when you're doing a computation, whether it's being done on a computer or just doing it in your head, you're going through a sequence of states and possibly making notes along the way. Eventually you'll hit a state where you're finally done and you gather up all your notes and finish your computation. So the field theory of computation tries to rank all the computations that could be in the world and say, you know, what's an easy one, what's a medium one, what's a difficult one, what's an impossible one. And so in the theory of computation, there is the idea of a language. So a language, kind of like a natural language like English or French, could be thought of as a dictionary of words. So, for example, in the English language, we have 26 letters in our alphabet. And if you take the letters in the alphabet and you arrange them in a certain pattern, you either will create a word that's in the English language, or you will create a word that is not in the English language. So if we were to write a program, is English, and you pass the word in, and this program either answers yes or no, whether or not the word is in English, then we would say I have a function in English, pass in dog, it answers yes. It accepts dog as a member of the English language. Is English XYZ? It would answer no. XYZ is not a word in the English language. If you put in boat, it would answer yes. Okay. Now there's other things about a natural language like syntax and semantics, which we're not really going to cover in computation theory. But, so for example, syntactically you can't say the, boat, dog, cat. You know, that's not English. You're saying a bunch of words, but they're not syntactically put together to form a sentence. And semantically is also meaning. You can't say the boat was barking loud, because the meaning of the word boat is it's something that doesn't bark. Right? But if you just think of a language as putting strings in and then answering yes or no, is it a member of the language? Depending on how complicated the language is, determines the complexity of that language. So computational complexity could mean how many states do we hop around in, and how many notes do we have to write along the way just to answer yes or no, is this word in our language. So, and it's also assumed, you know, this is the difference between algorithms and problems. You could have a problem like I want to go from the Jersey Shore to New York City. An algorithm will find a path that gets you from the Jersey Shore to New York City. You might have an algorithm that says go from the Jersey Shore, drive down to Miami, Florida, then drive across the country to San Diego, then up to San Francisco, and then drive back to New York. And that would be one solution to how to get from the Jersey Shore to New York City. But you wouldn't want to follow that one, and why wouldn't you want to follow that one? You wouldn't want to follow that one because it's not very efficient. So if you have a problem like how do you get from point A to point B, there could be many, many solutions to the problem. We're interested in finding the quickest solution, the most efficient solution, and then ask ourselves, how complicated is the computation to find the most efficient solution to a problem? So complexity is making the assumption you're going to find the most efficient solution to the problem. So very famous linguistic person named Noam Chomsky. Maybe you've heard of him, also politically very active. He arranged all the different types of computations from easiest to most difficult, and is the famous Chomsky's hierarchy of computations. And he arranged them as type 0, the most difficult, type 1, a little bit easier, type 2, easier than that, type 3, very, very easy. And the idea between the 4 levels is really how much computational equipment you need to perform the computation. So it's not focusing on time, it's how much equipment do you need. So like I said earlier, when you're doing a computation, you're moving around from state to state. The initial state, then you start going through a loop, doing some computation. You might be making notes for memory for later steps. So, according to Chomsky's hierarchy, I'll go from the most difficult to the easiest ones. The most difficult computations allow you to have as many states as you want to hop around to. And I'll go over an example of what a state is shortly. You can hop around to as many states as you want, and you get unlimited memory. Unlimited memory. So those are the most difficult problems, the ones where you can have as many states as you want, and as much memory as you want, and as much time as you want, and you have to just keep computing. If there's a restriction that the amount of memory you have must be linearly proportional to the size of the input string that you're trying to answer yes or no. Is it a member of the language? So that means if, let's say, the string is 10 characters long, you only get 10 or 20 or 30 units of memory to perform your computation. So you don't get unlimited memory. Like the type 0, you get limited memory. It's limited, it's proportional to the size of your input. Easier computations than that also have memory. You have a certain amount of memory, but you're not allowed to randomly access the memory. You can't just pick any part of the memory and say, I'd like to read this field, or I'd like to read that field. So you can stack up your memory, but you're only allowed to read the top element at any one computation. You can't go looking through the memory for a field that you're looking for. The easiest type of computation is the type 3. That's where you have a state machine. You're hopping around from state to state, not allowed to use any memory. So you're reading a string like dog, you read a D, you hop to a state. You read an O, you hop to another state. You read a G, you hop to another state. And at that point you have to answer yes or no, is this in the language? So the most difficult problems, when we have unlimited memory, are called recursively enumerable languages, and you have a theoretical Turing machine, the device that has unlimited memory, unlimited space. And a Turing machine is modeled on today's computers. Named after Alan Turing, famous, the father of computer science, some people call it. A linear bounded automata means you get a fixed amount of memory, proportional to the size of your input, and you can move from state to state and read, randomly access that fixed amount of memory. They call that a linearly bounded automata. And that can answer yes or no to languages that are context sensitive. The case where you have memory but you don't have random access to the memory, you can only read the top element on your stack at any given point in time. That's called a pushdown automata. So you have memory, but it's stacked up. And that's a type 2, and those accept languages that are called context-free languages. So if you want, you can look these up in take a theory of computation course, they'll cover all of this. The type 3 languages in Chomsky's hierarchy have a finite state automata. So you move around, and we're going to go over this in a second. Finite state automata, you read a letter, you move to a state. You read a letter, you move to a state. At the event, when you read the last letter, if you're in a yes state, you answer yes. If you're in a no state, you answer no. So a finite state automata is the type of equipment you use to do the computation, and the languages that accepts are called regular expressions. And that's really the topic of today's course, today's lecture. So here's an example of a finite state automata. It is traditional but not required that you have a certain number of states. This is a really simple example. It has two states, state 1 and state 2. And what you start doing is you start reading a string. And when you're done reading the string, you're going to answer yes or no, is this string in my language? That's all a regular expression is. Reads a string and answers yes or no. Is it in my language? So this arrow means this is the start state. And the alphabet to this state is zeros and ones. The only thing that it will accept as input strings is zeros and ones. So I'm at the start state, state 1. If the first thing I read is a 1, I stay at this state. If I read another one, I stay at this state. If I read 50 ones, I stay at this state. But if I read a 0 on my input, I go to this other state. Now, a double circle traditionally means we're going to answer yes, it's a member of our language. And a single circle means we're going to answer no, it's not a member of our language. So, I could read any number of ones, but if I read a 0, I go into a state where this is now not a word in our language. I can then read as many ones as I want, and I'm still not a member, the string is still not a member of our language. But if I read a second 0, all of a sudden it's now a member of our language. Then I can read a bunch of ones. But if I read a third 0, whoop, string's no good anymore. Then I can read a bunch of ones. But if I read a fourth 0, then it's good again. So what language are we accepting here? Let's look at some of these questions. So consider this finite state automata. What is the alphabet? The alphabet is zeros and ones, meaning I'm reading zeros and ones that I'm going to eventually answer yes or no if it's a member of our language. What words does this accept? Besides this state, how much memory? Am I making notes along the way? I'm not making any notes. I'm just bouncing, I'm reading an input character and I bounce to a state. No memory. So that's, if there's no memory, and it's just a state machine, that is a finite automata, and therefore this is a regular expression. If I have to use memory, it's not a regular expression, and that's not what we're talking about tonight. So, what strings does this thing answer yes to? And can anyone see the pattern? What strings are we answering yes to? No one? All right. Okay. The string can have as many ones as it wants, including 0. It could be an empty string, because I immediately start in a yes state. So even if there's no input, I say yes. A blank input is part of my language. I can have as many ones as I want, but if I have an odd number of zeros, string is unacceptable. If I have an even number of zeros, string is acceptable. So would 1, 1, 1, 0, 1, 1, 1, 0 be acceptable? Yes, because it has 2 zeros. Would 1, 0, 0, 1, 1, 0 be acceptable? No, because it has 3 zeros, and odd numbers of zeros don't count in this language. Okay. All right. Write a regular expression for this finite automata. So if I said, given this picture, write out on paper what it's going to accept and not accept. Well, the truth of the matter is, starting here, I could either read a 0 or 1 and I go to a different state. So I can write this out as a regular expression. My language, L, consists of, I could read 0 to as many ones as I want. So a 1 with a little star up here means 0 off to infinity, number of ones. Then I'm going to read a 0, followed by maybe as many ones as possible. Then I'm going to read a second 0, followed by maybe more ones. And I could repeat this double 0 thing over and over and over. As long as the number of zeros comes out even, I'm fine. So this is pictorially the finite state machine with no memory that accepts this language, this is the regular expression that describes this machine. This is how you'd write it out in theoretical computer science, not in JavaScript. JavaScript's a little different. Okay. So here's another example of a finite state machine. Not everybody uses the double circle to mean yes and the single circle to mean no. Some people put no, no, yes in the state. Some people, they copied this off the internet. Off, off, on. So on means in the language, off means not in the language. Okay, so what is this language doing? Here's our starting state. I can read as many ones as I want. Then I read a 0. That takes me to a second state. Still unacceptable. But if I then read a 1, I go back to this first unacceptable state. However, if I read a 0 and it is immediately followed by another 0, 2 zeros in a row, then my word is considered acceptable. But after I read 2 zeros in a row, if I read a third 0, I come back to here. And if I read a 1, I go all the way back to the beginning and start over. So, I'm reading a bunch of 1s. I read a 0 immediately followed by a second 0. Now the word is considered acceptable. If I read a third 0, it's unacceptable, but it's 1 more 0 away from being acceptable. So, what's going on in this finite state machine? If I read a 0 followed by a double 0 and the word ends, if it ends with 2 zeros, it's acceptable. If it ends with 2 zeros or 4 zeros, it's acceptable. If it ends with 2 zeros or 6 zeros, it's acceptable. If I see a 1, all the way back to the beginning. So this is a finite automata that will only accept strings made up of zeros and ones that end with an even number of zeros, 2 zeros or 4 zeros or 6 zeros or 8 zeros. So the string 1, 1, 0, 0, 0, 0, that's acceptable because it ends in 4 zeros. 1, 1, 1, 0, 0, 0, unacceptable because it ends in 3 zeros. 1, 1, 0, 0, 0, unacceptable. It has to end in an even number of zeros. And how could we write this as an expression? I could say 0 or 1. This star means as many times as you want. It could be 0 times or as many times as you want. And then it must end with 2 zeros. This plus sign means it must show up at least once, but could go off to infinity. So it could be 2 zeros, 4 zeros, 6 zeros, 8 zeros, but it must be at least 2. It must be at least 2. Okay. So just to recap, here's the computational equipment, a finite state machine, no memory. I start here, I read an input character, I jump to another state. I'm not recording any notes along the way. Read another character, jump to another state. When the string runs out, if I'm in a yes state or an on state, I answer yes, it's in the language. If I'm in an off state, I answer no. Here's how we write the regular expression for this language. Okay, now, in JavaScript, we can have a function like this. We can have a function that says, I have a string, Java space script, Java in capital J. I can have a pattern, another string. I'm going to start my regular expressions with a slash. I'll say Java in small letters, and I'll end it here, and then I means I'll include any case insensitivity. So don't worry about case. Tell me that you found this substring. I can now say result, a variable result. Take the string and match it against this pattern. does this pattern show up as a substring inside of this string? If so, answer yes. Right? So I get this element, I get the demo element, and I print out the result. So basically what I'm looking for in my result is a yes or no. Does this pattern appear somewhere in that string? So I'm doing substring search. Okay, this is unfortunately, so this is a cheat sheet for all the different ways that we can write regular expressions. It's kind of small, so you might not be able to see it, but you can just pull up the PowerPoint. It's a good cheat sheet for you to use. Okay, so here's an example. Suppose we wanted to validate, somebody gives us, you have a website, somebody enters an email address, and before you store it in your database, you'd like to validate, is this a real, legitimate email address? Well, we could read character for character from left to right, and when we get to the last character, we answer yes or no, it's valid or it's invalid. So we can create a regular expression to describe that. So we could create a function in JavaScript called email is valid. It's going to answer true or false. So someone passes in an email address, and then what we're going to do is we're going to validate it. We're going to run it through a regular expression, read each character for character. When we get to the last character, we're going to answer yes or no, true or false. So the regular expression starts with the slash, it's backslash, so we'll go / capital S, this is on the cheat sheet. Capital S means any character that's not a white space. The plus sign means I need at least one, but I could have up to infinity non-white spaces. I then want to see an @ sign. And so this escape means it's a special character. I'm not looking for capital S, I'm looking for any backslash, look on the cheat sheet, and it's a non-white space character. The plus means at least one, but could be many. Then I want to see an @ sign. Then I want to see another backslash S, more non-white space. The plus sign means I want to see at least one. Then I'm doing an escape period. I want to see a period. So it's going to be like student at college, period. And then more stuff, more non-white space stuff after that. So the method test is a Boolean, yes or no. If I took this email address that someone passed in, and I ran it against this regular expression, I'm basically creating a language here, and I'm asking, is this email address, yes or no, a member of my language, my regular expression language? If it answers yes, that means it's a legitimate email, or it could be not legitimate. It's not a great email tester, but at least it's something. It's better than accepting anything. All right, so suppose a couple other things we could do with regular expressions, which are typically nicknamed Regex, faster than saying regular expressions. We can have a string that says hello world, and then we can have an index that says take the string and do a search on the word world. Go through the string and see if you see WORLD anywhere as a substring in here. And if so, return the integer where it starts. So this is index 0, 1, 2, 3, 4, 5, 6. So this would return a 6. I found the string, and it's at location 6. Okay. We could do replacements. If we take an input string and run it through a regular expression and it finds something, we could replace it with something else. So I could have a string that says, school is open today, and then I could say, take my string and replace anywhere I see open. So this is really a regular expression. I'm saying, read through the string, and if you see an O, go into a state that means I just read an O. So I read this, I read this, I read this, I see that first O. Ooh, it looks like I'm starting to spell open. Then the very next letter is not a P, so I go back to the first state, meaning you gotta start over, there's no open here. And then I go to the next one, next one, next one. I see an O here. Oh, I just read an O. Is it followed by a P? Oh, yes, it is. Is it then followed by an E? I go to another statement, another state. So this would be like 4 states in a row. O, P, E, N. Once I see that N, I'm answering yes. Doesn't, anything after that, zeros or ones, I'm going to stay in my yes state. So once I find it, I replace closed, and then I can print out the result. School is closed today. So I could do find and replace. Okay, yeah, so this is a couple, again, this is more like cheat sheet stuff, but a small I means, don't worry about case, find me matches, but don't stop because of cases. A G would be a global match, and an M you could put at the end of a regular expression, say, look for it on multiple lines. If we say A, B, C, that means I'll take any one of those characters. If I want to say any character between 0 and 9, I could say 0 hyphen 9. That's the same as saying 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I say X or Y, that means I'll accept either one. Other popular meta characters, \D is any digit between 0 and 9. \S will find white space. Small s is white space, capital S is non-white space, the opposite. B means, \B means it has to be at the end of the word, and could also use hexadecimal numbers. Okay, and then this is a common notation. N plus means I want to see at least one N, but it could be more than one N, but it's got to be a minimum one. And star means I want to see 0 or more N's. Could be 0. Okay, and then, and question mark matches any string that contains 0 occurrences of N. 0 or 1 occurrence of N. No more than 1. Okay, so regular expression, right? We have it now. This is, you can cut and paste this and run this in a browser to test it out. So what we can do here is I can create an object and say my regular expression is life, and then I'm doing .execute, and I'm saying the best on the string, the best things in life are free, and I can go searching for this for the substring life, and I find it. And then I can print out a found object 0, which is the index. I'm sorry, object 0 is going to be life, the pattern we're looking for. In position, the index will print out where it is. Which would be like 6, 7, 8, 20, right? Found life at index 20 within the string. Best things in life are free. Okay, all right. So suppose now we're back to the email example. We had a regular expression that detects emails, but it wasn't the greatest one in the world. So let's make it a little bit better. We have an email address, student@college.edu. We will find it acceptable. We'll answer yes if the regular expression with this /, capital S, any non-space characters, I want at least one, maybe more. And then I want it to end in either com or edu. I'd like to end it. Okay. And then I'm going to do a test. Test is going to answer yes or no, is it in the language? I put my email in, compared to this regular expression, it answers yes or no. That's it. This is very weak. Okay. Okay. So now, suppose you use this regular expression, and your input was not .edu, but was .education. Would this regular expression answer yes or no? And the answer is it would. It would. Because I never said it has to end in edu. All I said was I want to see non-space characters. I've got a bunch of them here, including the @ sign, all the way up to here. And then I saw edu, and I never said it had to end in edu, and then I saw more stuff. So this would be considered acceptable, and we don't want that. So we need to make our string a little bit better. So we can do starts with and ends with. Okay, so we have an email address, student at college education. And we say hat or caret, whatever you call this thing. It must start with, not just some substring somewhere in the middle, it must start with non-white space characters, at least one of them, and it must end, $, must end with either com or edu. That's a little bit better. It's still not a good, it's still not a good regular expression for testing emails, but it's a little bit better. It's not just doing any random substring. So we'll revisit it again, make it even a little bit more better in a second. Suppose somebody wanted to tell us what time of day it is, and we wanted to validate with a regular expression if they're giving us legitimate numbers. So here's a valid input, 12:34 p.m. or a.m. Here's a bad one, 12:34:05. That doesn't make sense. Okay? So we can have a regular expression. We start our regular expression. It must begin with a digit, followed by a digit, followed by a semicolon, followed by a digit, followed by a digit, and it must end that way. It must end with 2 digits. It must start with 2 digits, have a semicolon, must end with 2 digits. So if we wanted to test the first one, it would say this one's a legitimate time of day, and this one is not. So I'm going to say, oh, right, this is a great regular expression to validate times of day, right? Well, what if you gave it the time of day 96:73? It's going to say, yes, that's a legitimate time of day, because all we care about is it starts with 2 digits, a semicolon, and ends with 2 digits. That meets the criteria, but that's not really a good time of day, right? So we want to make a regular expression a little bit better. How about this? We'll make a regular expression start with 0, 1, or 2. So this would be a 24-hour clock. The next digit could be any number between 0 and 9, then a semicolon. Then for the hours, it could be any number between 0 and 5. And then for minutes, it could be any number between 0 and 9. That looks better. That rules out, that answers no to a lot more times that are not good. So it'll answer no to 96:78, but it will answer yes to this, 29.59. Because we said any number between 0, 1, and 2 is acceptable for the first one, And then any number between 0 and 9 is acceptable. There is no 29th hour in a day. So it's still letting unacceptable values through. So we still need a better regular expression than that, but we're improving on it. Okay. All right, back to email addresses. Suppose we had an email address, student@college.edu. We can accept strings that start with non-white space characters, and we have at least one, but maybe several, an @ sign, followed by more non-white space characters, at least one, followed by a period, followed by com or education, and it must end with com or education. Oh, that's much better. Now, I'm writing this out. I'm breaking this, so this looks a little ugly. When you first start seeing JavaScript regular expressions, they look ugly. They have to be put together like this. I spaced it out here just so we can see what's going on, but you're not allowed in JavaScript to put these spaces because now you're saying I want to see blanks in my email address. So I'm just spacing it out to say, here's where it starts. It must begin with at least one regular non-blank space, must be an @ sign, must be more, at least one non-white space, must have a period, and then must end in .com or .edu. And that's the end of it. Okay. So I spaced this out for readability, but you're not allowed to do that. You have to put these together, otherwise now you're accepting blank spaces in your regular expression. So what you want to get good at is reading something like this and knowing, oh yeah, I can see what's going on. Okay. Oh, sorry. All right, so that's as far as I want to go. So now, as far as regular expressions that handle email addresses, if you Google JavaScript regular expressions for email addresses, There is currently no perfect answer for this. There's so many different .com, .edu, .club, .us, country extensions after the .com, and so many different ways of what could be before the @ what could be after the @ So you'll see people, you'll see websites that have regular expressions for email addresses. And they'll say, oh, this handles 99% of the cases, but it never quite handles 100% because email addresses are always changing. There's new acceptable email addresses that weren't acceptable a year ago. So if you're building a website and you want to validate an email address before someone submits it, it'd be nice to have a very rigorous regular expression, but it's really going to be difficult to do that forever, have it be perfect. So, okay, so and